So we continue our discussion about modules, and we'll also see some Macaulay examples. Okay, so the first thing that we would like to observe using the home module that we saw last time, which is f from M to N such that f is R linear. The set of R linear maps from M to N. Okay. So suppose we had N1 to N2. This is some phi, N2. Okay. And we have a map from M to N. This is some f. Okay. If we compose this, we would get a map like this. Okay. So this is the composite. Okay. And so what it does is, think of this as something fixed, that N1 to N2 is some fixed map. Then for any f, there exists a map here, which is the composite. Okay. So what have we obtained? We have obtained a map from home Mn1 to home Mn2. Okay. Let's call this map phi over star. Okay. And phi over star of some f is, you first apply f to get to N1 and then you apply phi. Okay. So this is the definition of what phi over star means. Okay. And one can check that this is R linear. So this itself is, so remember these are R modules and this is an R linear map. Okay. So one can okay, so given this data, one gets, for every m, one gets a map like this. Okay. So this is one observation. Okay. So now we would like to discuss something called define what is called an exact sequence. A sequence of R modules N1 to N2 to N3 is exact. So here, so whenever we say exact, it only applies at a place where there's a map coming in and a map going out. Okay. So so right now, sorry, I'm just trying to define this term, exact. Okay, and this is at N2. One cannot talk about exactness here or there, the way we have. If, sorry, we need some names for these things. Call this thing F and call this G. Okay. Kernel of G is image of F. Okay. So this is what we have. So 0 to N to N1 exact means it's exact at this point, because that's the only place where there's a map coming in and going out, if and only if, so let's call this map F. There's a unique map from 0, this is the 0 map, if and only if F is injective. Okay. Similarly, some N to N1 to 0 exact, again exact in the mid out here, that's the only place where the question makes sense, if and only if, again let's call this map F, F is surjective. Okay. And given N inside M, okay, we get an exact sequence 0 to N to M. That is just to say it is a submodule, this is injective, and then M mod N to 0. So this just says it is surjective. So this much says N is a submodule, this much says M mod n is a quotient module. Okay. And the middle part says, so maybe it's better to have, okay, middle part, so let's label this map f and g. Middle part says kernel of G. The middle part says kernel of G is image of f, which is precisely what it is. The kernel of M to M mod n is n. Okay. So given a submodule inside a module, we get an exact sequence like this. Such a thing is called a short exact sequence, to say that, to denote that there are only at most three non-zero terms. The left 0 is to prove, to indicate that this is injective. The right 0 is to indicate that this is surjective. Okay, so such a thing is called a short exact sequence. So if you remember what we did in the finite presentation, so M finitely presented. One does not. I'm just finitely presented. Sorry, this is finitely presented. Okay, M is finitely presented means that there exists an exact sequence. Just restating what we knew from there, exact sequence F2 to F1 to M to 0 with F1 and F2 free of finite rank. Both are free and of finite rank. Okay, so this is the this is just restating what we know in this language. Okay, so one reason one would like to study such things is the following proposition. Let M be an R module. Okay, then the following are equivalent. 1. Every submodule of M is finitely generated. 2. Ascending chain condition holds for M, for submodules of M. Okay. And 3, every non-empty collection of submodules has a maximal element. Okay. So ascending chain condition means similar to what we discussed for modules, for ideals. If you have M1 inside M2 inside, let's call it an ascending chain, then there exists M such that for all n greater than or equal to M, Mn is equal to Mn. After a while, it stays constant, and this. So the proof is the same, identical to the proof the one that we did for ideals. So this is an exercise, okay. And then now we define M is said to be Noetherian. So we're not saying anything about R, we're just saying M is Noetherian. So M is, we can say M is a Noetherian R module if the conditions above hold for M. I mean, if any single one holds, the other two also will hold. So any one of them holds for M. Okay, so then M is said to be Noetherian. Okay. So why did we set up all, I mean, one of the reasons it's sometimes easy to describe in terms of exact sequence is the following proposition. Let 0 to M1 to M2 to M3 to 0 be an exact sequence, short exact sequence. Short because there are only three, at most three non-zero terms. Then M2 is Noetherian if and only if M1 and M3 are Noetherian. Okay, proof is an exercise, not very difficult. Okay. If M2 is Noetherian, every submodule is finitely generated. A submodule of M1 is also a submodule of M2. So every submodule of M1 is finitely generated. Similarly, if you have a submodule of M2, its inverse image here will be a submodule of M1, and then you can that is finitely generated, and that finite generating set is enough to generate its image inside M3. And then you have to work a little bit to prove the other direction. So all that is an exercise. Okay, so now, okay, just one remark. R is a Noetherian ring. This is something that we defined a while ago to mean that every ideal is finitely generated if and only if it is a Noetherian module over itself. I mean, if you consider it as a module over itself, then it is a Noetherian module. Okay. That's because the submodules of R, the R submodules of R are precisely the ideals. Okay. So in the study of in commutative algebra as well as its applications to algebraic geometry or number theory, it is the Noetherian rings and finitely and Noetherian modules are quite important. Okay. So here is a proposition which gives us a large class of Noetherian modules, which are also, I mean, important in applications. Okay, so let's say R is a Noetherian ring, M an R module. Okay, then the following are equivalent. 1, M is Noetherian. 2, M is finitely generated, and 3, M is finitely presented. Finitely presented. So there are some implications that are immediate from the definitions. If M is Noetherian, then M is already, every submodule of M is finitely generated. So in particular, 1 implies 2. M itself is a submodule of M, so it is finitely generated by definition. Similarly, finitely presented assumes it's already finitely generated, so that implies 3 implies 2. Hence, we need to show that 2 implies 1 and 2 implies 3. So before that, we need to show that 2 implies 1 and 2 implies 3. So the key, what do we know about a finitely generated R module? That there exists a finite rank free R module F with a surjective map F to M. Okay, so this is what this is what hypothesis 2 tells us. Okay, so to show that, okay, so the first observation that we would like to make is F is Noetherian. Why is that so? So this is induct on the rank of F. Okay. By assumption, if rank of F is 1, then F is isomorphic to R, which is Noetherian. Okay. Otherwise, there exists an exact sequence, so this you should prove, okay, and you will prove that this is what is called a split exact sequence. Okay, with F1 free of rank equals rank of F minus 1. So it's exactly like vector spaces in this situation. Okay. So this is Noetherian, and in the previous proposition, therefore we can conclude that this is also Noetherian. So this is Noetherian, and therefore F is Noetherian. Therefore, I mean this is okay. So any finitely generated free rank is Noetherian, and since M is a quotient of, so now back to the proof, since F, there's a surjective map, since there exists a surjective map onto M is Noetherian. Okay. Now let's call this map phi. What about kernel of phi? Is an R submodule of F, so it is finitely generated. That's because F is Noetherian. Again, we are using the fact that F is Noetherian. Okay. And therefore, we conclude that, so therefore there is an F2 of finite rank, free F2 of finite rank, such that F2 surjects onto the kernel of phi, and we take, okay, so therefore M is finitely presented. Okay. So this is the proof that the three notions over a Noetherian ring, the three notions of a module being Noetherian, module being finitely generated, and module being finitely presented are the same. This is an important situation where many questions that we would like to understand or study, the situation would be some variation of this thing. Okay. So let's look at a Macaulay example. Here, again, let me just emphasize, this first line should be just ignored altogether. This is part of the code, the part of the program that writes the code, takes the output and writes the documentation. So just ignore that altogether. And this is the input part, the one that is the offset from the left is input. Macaulay 2 input. Okay, and this is the so this much in typesetter font is the output. Okay, so this is so ignore this thing altogether. Okay, so this is so similarly this is the input. That's just some comment line at the top. Ignore that. So let's see, what are we doing? We give R to be a polynomial ring in two variables. Okay, some finite field small enough where all computations will be done quickly. Then the way we specify a free module is a caret and a number. So this is a free module of rank 2. Then we ask, is free module? So this is a function which takes an input module and returns Boolean output, and here it says it is free. So then we ask, is free module R? It says false, and why? Well, R itself is a polynomial ring. It's not a, right? So R itself is a polynomial ring, okay, not a module. I mean, the type of R in Macaulay is R, and so we have to give R to the 1. So we ask, is free module R, R caret 1 like a superscript? Then it says it is true. Okay, so one can verify this using the command to check what the type of some quantity is class, okay? And if you check this, you will get these two. Okay? Sometimes if some functions give unexpected answers, it's a good idea to check these things. Or if you're using a function, then it's better to check what sort of types are the input, what type the input should have, and we're going to use output what type it has. Okay, okay, so now we can define, okay, so we saw earlier that if you have a finitely presented matrix, finitely presented module it can be written as a co-kernel of a matrix. So here this is what we do. We define an f to be a map to the free module R2 from the free module of rank 1. So remember, the map arrow is always from the right to left in Macaulay. And so this is a matrix. It's a matrix. So a matrix is a list of lists. Each individual list in the list is the rows. So this is a 2 by 1 matrix. Okay, so here it's 2 by 1 matrix, and so this is what it does. And yeah, so here it just constructed the co-kernel of this matrix. We can, given a matrix, we can ask for its presentation matrix. These are over Noetherian, so anything finitely generated is finitely presented. So it will tell us of the presentation matrix. So here we define I to be an ideal of R, and we write this command called module of I, which is to construct the module corresponding to I. It's the same abelian group, but now its type has changed to module, and it's something new. Okay, so these are required so to keep. Then we write R1 module of I. So this is again, this is still R mod I, but now thought of as a module and not a quotient ring, and we ask for its presentation matrix. And here the ideal I was the ideal generated by the variables of R. So it is the maximal ideal in this case. It is a maximal ideal in this case, and here we get R module, R submodule of R1. Okay, sorry, I jumped. So the output of module I is this thing. So if we give I, so it's an ideal of R. Then we ask for module of I. It's an image of this R submodule of R1. Then we asked R to the 1 module of I. Then it said R module quotient of R1, and it just gave the matrix for which it is a quotient. It said it's a co-kernel, and then we asked for its presentation matrix. It showed us a matrix. Okay, so this is. Okay, now another curiosity, for us. Okay, so again, just ignore this part. So we ask here, this is the input line, hom from R4 to R5. What is it? It says R20. It's a free module of rank 20. Okay, so this you will do as an exercise. If you have a free module of rank A and a free module of rank B, hom between them is of rank A, free of rank AB. This will be one of the exercises. Let's discuss a few more things. If you have an ideal, so I and R ideal, M and R n R modules. This means I also implicitly mean that it is an R submodule, not just a subset. Okay? So if we have this, then we can define M mod IM. So observe that IM is, so this, what is this? This is the submodule of M generated by things of the form R times X, where R is inside I and X is inside M. So it is like taking the square of an ideal, but here it's two different, one is an ideal, one is a module. Again, just taking the products is not going to give us a submodule. We have to take the submodule generated by them, meaning finite linear combinations of those things. Finitely R linear combinations of such things. Okay. This R here is from I, but when you take combinations, the coefficient can come from R. Okay, so this is, and M, so this IM is a submodule, so we can talk about M mod IM is an R mod I module in a natural way. Okay. And if we have the, so we had N to M, okay. So we had an exact sequence 0 to N to M mod IM to 0. Okay. So we had this exact sequence, to M mod N to 0. Okay. So now what if we further go modulo the submodule generated by I inside them. Okay. So we will get M mod IM here. Okay. So here we will have M mod IN, but this need not be injective. Okay. And then out here we would have M mod N. N has already been set to 0. So in addition we are setting IM to 0. So this exact gives. Okay. Notice that this was injective, but here there is no guarantee that this is injective. Okay. But one would get such a sequence. Let's look at one more Macaulay case. So just one thing that I needed to explain while using Macaulay here is what the notion of what is called a sub-quotient. Okay. So there is a help page on sub-quotients, so please read that. Let's just quickly explain with an example. Here just again ignore this line, and so R is just a polynomial in two variables. I is the ideal generated by the variables. Then we ask I mod I squared. I mod I squared is not an ideal. So it is written as sub-quotient of this, and it's given two matrices, and then it's written sub-quotient, and it says R module sub-quotients of R1. So what exactly does that mean? Okay. So let's take a map phi from a free module of rank 2, basis F1, F2, and basis E here. Okay. So rank 2 here and rank 1 here, in which this matrix describes the map. In other words, F1 goes to X times E and F2 goes to Y times E. That's what the first matrix here means. Similarly, here it's a map from rank 3 to rank 1. So G1, G2, G3 basis and same E. Okay. So this is G1 goes to X squared E, G2 goes to XYE, and G3 goes to Y squared E from here. And notice that the image of the second map, psi, is inside the image of phi, and both of these are submodules of R1. The map has target R1, so the image is a submodule, and it says I mod I squared is the quotient of the submodule, the larger submodule by the smaller submodule. That's what it's called, a sub-quotient, and this is a way Macaulay describes many modules, and one can convert it to the usual description of quotients, co-kernel of a map. There are commands to that we will do it, and as we proceed we will see these things. Okay. So this is the end of this lecture.